Welcome. Get comfortable. Let the weight of the day settle, and let your breathing slow. Tonight, we are going to talk about the very beginning of everything. Not the beginning of your day, not the beginning of a story, but the actual beginning. The moment the universe itself flickered into existence. There is no rush. We have all the time in the world. After all, the universe took nearly 14 billion years to get to this point. We can take an hour. This is a question that human beings have asked for as long as we have been able to look up at the sky and wonder. Where did all of this come from? The stars, the planets, the empty space between them. The air you are breathing right now. The atoms in your bones. Everything you have ever touched, everything you have ever seen, every particle of light that has ever reached your eyes, all of it came from somewhere. And that somewhere, as far as we can tell, was a single, impossibly hot, impossibly dense point, smaller than an atom, that expanded into everything we know. That idea might sound strange. It might sound impossible. But over the last century, scientists have gathered evidence from every corner of the cosmos, and it all points to the same extraordinary conclusion. The universe had a beginning. And that beginning was the Big Bang. So settle in. Let the words wash over you. You don't need to memorize anything tonight. You don't need to take notes. Just listen and let the story of creation carry you gently toward sleep. Before the beginning. Let us start with the hardest question of all. What was there before the universe began? The honest answer is that we do not know. And that is okay. Some of the most brilliant minds in physics have wrestled with this question, and the truth is that our current understanding of the laws of nature breaks down at the very first instant. Time itself may not have existed before the Big Bang, which makes the word before almost meaningless in this context. Imagine trying to ask what is north of the North Pole. The question feels like it should have an answer, but it does not. There is no direction called north once you are standing at the very top of the earth. In the same way, asking what came before time began may not be a question that has an answer. It is not that we are too ignorant to find the answer. It is that the question itself may not apply. But that has not stopped physicists from trying. Some theories suggest that our universe may be one of many, a single bubble in an infinite sea of universes, each with its own laws of physics. Others propose that the universe cycles endlessly, expanding and then collapsing and then expanding again, like a cosmic heartbeat that has been beating forever. Still others suggest that the universe emerged from a quantum fluctuation, a tiny ripple in the fabric of nothingness that grew into everything. These are beautiful ideas, and perhaps one day we will know which, if any, of them is correct. But for now, let us focus on what we do know. And what we know begins at a moment so brief, so unimaginably small, that it makes a single heartbeat feel like an eternity. The first fraction of a second. The universe, as best we can tell, began approximately 13.8 billion years ago. But when we say began, we are talking about something that happened faster than you can possibly imagine. The entire character of the universe was determined in a fraction of a second so small that there is no human experience to compare it to. Let us try anyway. 1 second. You know what a second feels like. A blink of an eye. A single heartbeat. Now divide that second into 1,000 pieces. Each piece is a millisecond. That is how long it takes a hummingbird to beat its wings once. Now divide that millisecond into 1,000,000 pieces. Each piece is a nanosecond. Light, the fastest thing in the universe, can only travel about 1 foot in a nanosecond. Now keep dividing. A trillionth of a second. A quadrillionth. Keep going. The events we are about to describe happened within the first tiny fraction of a second, so small that writing it out would require more zeros after the decimal point than there are atoms in your body. At the very first moment, the universe was unimaginably hot. Not hot like a summer day. Not hot like the surface of the sun. The temperature was something like 10 to the power of 32 degrees. That is a 1 followed by 32 zeros. At that temperature, the familiar laws of physics as we understand them did not yet apply. The four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were merged together into a single, unified force. Everything was one. This is a concept that physicists call the Grand Unified Epoch. And it lasted for an almost inconceivably brief moment. Then, like ice crystals forming in cooling water, the forces began to separate. Gravity peeled away first. Then the strong nuclear force separated from the electro-weak force. Each separation released enormous amounts of energy, and the universe changed its character with each one. Let us pause for a moment and appreciate what this means. The force that holds you to the earth, gravity, and the force that lights up your phone screen, electromagnetism, were once the same thing. The force that holds the nucleus of every atom together and the force that governs certain kinds of radioactive decay, they too were once united. In the very beginning, there was no distinction between any of these forces. The universe was simpler then, more elegant, more unified. And as it cooled, that unity shattered into the diversity of forces we experience today. It is as if the universe began as a single, pure note and gradually became a symphony. You do not need to remember these names. Just picture it like this. Imagine a single drop of water, perfectly still, perfectly uniform. Then imagine that drop beginning to crystallize, forming intricate patterns as it cools. That is something like what was happening to the universe in those first moments. Simplicity was giving way to complexity. Uniformity was giving way to structure. The universe was waking up. Inflation, the universe expands. And then something truly extraordinary happened. In a period lasting less than a billionth of a billionth of a billionth of a second, the universe expanded at a rate that defies comprehension. This is called cosmic inflation, and it is one of the most remarkable ideas in all of physics. Before inflation, the observable universe, everything we can see with our most powerful telescopes, was smaller than an atom. After inflation, it was roughly the size of a grapefruit. That may not sound like much, but consider the scale of that change. It would be like taking a grain of sand and expanding it to the size of the observable universe. And it all happened in a time interval so short that light could barely cross the width of a single proton. Why did this happen? The leading theory involves something called the inflaton field, a kind of energy field that permeated the early universe and drove this rapid expansion. As the inflaton field released its energy, it pushed space itself outward at speeds far exceeding the speed of light. Now, you might be thinking, I thought nothing could travel faster than light. And you are right, nothing can move through space faster than light. But space itself can expand as fast as it likes. There is no speed limit for the stretching of the fabric of the cosmos. Inflation solved several deep mysteries about the universe. It explained why the universe looks roughly the same in every direction, because regions that are now billions of light-years apart were once close enough to exchange information before inflation pushed them far apart. It explained why the universe appears to be geometrically flat, stretched smooth by the incredible expansion like the surface of a balloon being inflated to enormous size. And it explained where the seeds of all future structure, every galaxy, every star, every planet, ultimately came from. Those seeds were quantum fluctuations, tiny random variations in the density of energy that existed in the universe before inflation began. Inflation took those microscopic ripples and stretched them across the cosmos, turning them into the slight variations in density that would eventually, over billions of years, grow into the galaxies and clusters of galaxies that we see today. The largest structures in the universe began as the smallest possible variations in the quantum world. There is something deeply beautiful about that. Let this idea settle into your mind like a warm blanket. Everything you see when you look up at the night sky, every galaxy, every cluster, every vast empty void between them, all of it was written in the quantum foam of the early universe. The blueprint for the cosmos was drawn in the first fraction of a second, and the universe has been following that blueprint ever since, building itself slowly, patiently, over billions of years. It is a story of extraordinary patience. And patience, as you lie here tonight, is something worth appreciating. The universe cools, a soup of particles. After inflation ended, the universe was still extraordinarily hot, but it was cooling rapidly. And as it cooled, something wonderful began to happen. Particles began to form. In the first moments after inflation, the universe was a seething, roiling soup of energy. Photons, the particles of light, were so energetic that they could spontaneously create pairs of matter and antimatter particles. A photon would transform into an electron and its antimatter twin, a positron. Then the electron and positron would collide and annihilate each other, turning back into a photon. This was happening constantly, trillions upon trillions of times, everywhere in the universe, all at once. But as the universe expanded and cooled, the photons lost energy. Eventually, they no longer had enough energy to create new particle pairs. The creation stopped, but the annihilation continued. Matter and antimatter particles found each other and destroyed each other in flashes of light. And here is one of the great mysteries of physics. For reasons we still do not fully understand, there was a tiny imbalance. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. Just one extra particle in 1,000,000,000. When the annihilation was complete, all the antimatter was gone. And that tiny surplus, that 1 in 1,000,000,000 excess of matter over antimatter, is everything you see around you today. Every star, every planet, every atom in your body. You exist because of a slight imperfection in the symmetry of the early universe. If the balance had been perfect, there would be nothing but light. No matter, no stars, no planets, no life. Just an endless sea of photons, cooling forever in an empty universe. Take a moment to sit with that. Everything that exists, every mountain, every ocean, every living thing, is here because of a tiny imbalance so small that if you tried to represent it, you would need to write out 1,000,000,000 zeros before you got to the one that made all the difference. And nobody knows why. This is one of the great unsolved puzzles in physics, known as the baryon asymmetry problem. Some process that we do not yet understand, tipped the scales ever so slightly in favor of matter. Without that tipping, the universe would be a perfectly symmetric, perfectly balanced, and perfectly empty place. Just light, forever. Instead, that tiny imperfection gave rise to everything. It is one of the most humbling ideas in all of science. The universe as we know it is the product of an imperfection, a flaw in the symmetry of nature, and that flaw is the reason you exist. The first 3 minutes, forging the elements. By the time the universe was about 1 second old, it had cooled enough for protons and neutrons to exist as stable particles. These are the building blocks of atomic nuclei. Protons are positively charged, and neutrons carry no charge at all. Together, they would eventually form the hearts of every atom in the universe. But that was still some time away. At around 3 minutes after the Big Bang, something remarkable happened. The temperature had dropped to about 1,000,000,000 degrees, roughly 70 times hotter than the core of our Sun, but cool enough for protons and neutrons to begin sticking together. This process is called Big Bang nucleosynthesis, and it is one of the great triumphs of modern cosmology. In those few minutes, the universe became a nuclear furnace. Protons and neutrons collided and fused together, forming the nuclei of the lightest elements. Most of what was produced was hydrogen, the simplest element, made of a single proton. About a quarter of the matter, by mass, became helium, made of 2 protons and 2 neutrons. And tiny traces of lithium and deuterium, a heavier form of hydrogen, were also created. That was it. Just hydrogen, helium, and a whisper of lithium. No carbon. No oxygen. No iron. No gold. None of the elements that make up the earth, that make up your body, that make up the air you are breathing right now. Those heavier elements would come much later, forged in the hearts of stars that had not yet been born. But we are getting ahead of ourselves. After about 20 minutes, the universe had cooled too much for nuclear fusion to continue. The window had closed. The cosmic furnace shut down, and the proportions of hydrogen and helium were locked in. And here is the beautiful part: when scientists measure the ratio of hydrogen to helium in the oldest, most pristine parts of the universe, the numbers match the predictions of Big Bang nucleosynthesis almost exactly. The theory tells us what those first few minutes should have produced, and the universe confirms it. This is one of the strongest pieces of evidence that the Big Bang actually happened. The chemical composition of the cosmos is a fossil, a relic of those first few minutes, preserved across nearly 14 billion years. There is something almost tender about this. The universe, in its first few minutes of existence, was already creating. It was already building. It did not yet have stars or planets or life, but it was laying the foundation. Hydrogen and helium. The 2 simplest elements. The raw materials from which everything else would eventually be made. It is like watching someone prepare the ingredients for a meal that will not be ready for billions of years. The universe was cooking, slowly, patiently, and it had all the time it needed. The Dark Age, a universe in fog. After the first 20 minutes, the universe entered a long, quiet period. The nuclear reactions had ended, but the universe was still far too hot for atoms to form. Electrons, carrying negative charge, were flying freely through the cosmos, unable to settle into orbits around the positively charged nuclei. The universe was a hot, dense plasma, a kind of glowing fog that light could not travel through. Imagine trying to see through a thick cloud. Photons, particles of light, would travel only a short distance before colliding with a free electron and bouncing off in a random direction. The universe was opaque. If you had been there and somehow survived the incredible heat, you would not have been able to see your hand in front of your face. Light was trapped, scattered endlessly by the sea of free electrons. This continued for about 380,000 years. That sounds like an enormously long time, and by human standards, it is. But in cosmic terms, it was just the opening act. The universe was waiting, cooling slowly, degree by degree, approaching a critical moment. During this time, the universe was remarkably uniform. Almost the same temperature everywhere. Almost the same density everywhere. But not quite. Those tiny fluctuations from the inflationary period, the quantum ripples that had been stretched across the cosmos, were still there. Subtle variations in density, slightly hotter here, slightly cooler there, slightly more matter in one region, slightly less in another. These variations were incredibly small, just 1 part in 100,000. But they were there. And they were patient. They would eventually become the seeds of everything. Recombination, the universe clears. About 380,000 years after the Big Bang, the universe had cooled to roughly 3,000 degrees. That is still very hot by everyday standards, about half the temperature of the surface of the Sun. But it was cool enough for something extraordinary to happen. Electrons, which had been flying freely for hundreds of thousands of years, finally slowed down enough to be captured by atomic nuclei. Protons grabbed electrons and became hydrogen atoms. Helium nuclei grabbed their electrons too. For the first time, the universe was filled with neutral atoms. Physicists call this moment recombination, although it is a slightly misleading name, since the electrons and nuclei had never been combined before. It was really the first combination. But the name has stuck. And with recombination came a transformation so profound that we can still see its effects today. When the electrons were captured by nuclei, there were suddenly no more free electrons for photons to bounce off of. The fog lifted. The universe, which had been opaque for 380,000 years, became transparent. Light was free to travel, unimpeded, across the cosmos. The light that was released in that moment is still traveling today. It has been stretched by the expansion of the universe from visible light into microwaves, but it is still there, filling every corner of the cosmos. We call it the cosmic microwave background radiation, and it is one of the most important discoveries in the history of science. If you could see in microwaves, you would see this light everywhere you looked. It comes from every direction, nearly uniform, with a temperature of about 2.7 degrees above absolute zero. It is the afterglow of the Big Bang, a baby picture of the universe taken when it was just 380,000 years old. And when scientists map this radiation in exquisite detail, they find those tiny fluctuations, the quantum ripples from inflation, imprinted in the pattern of slightly warmer and slightly cooler spots. It is like looking at the ultrasound of a universe that has not yet formed its stars and galaxies, but carries within it the blueprint for everything that is to come. Take a breath. Let that settle. The light from the beginning of the universe is still here. It is passing through you right now, as you lie there listening. You are bathed in the oldest light there is. The cosmic dark ages. After recombination, the universe entered a period that astronomers call the cosmic dark ages. This is not the same as the dark ages of human history. This was a time when the universe was truly dark, in the most literal sense. There were no stars. There were no galaxies. There was no light being produced anywhere, except for the fading glow of the cosmic microwave background, which was steadily redshifting into invisibility as the universe expanded. The universe at this time was a vast, quiet expanse of hydrogen and helium gas, slowly cooling, slowly expanding, drifting in darkness. If you could have stood in the universe during the Dark Ages and looked around, you would have seen nothing. Absolute blackness. A void so complete that it is almost impossible to imagine. But the universe was not truly empty, and it was not truly still. Those tiny density variations, the ones that had been imprinted during inflation and revealed in the cosmic microwave background, were slowly, quietly growing. In regions where the matter was slightly denser than average, gravity was gently pulling more matter inward. The denser regions were getting denser. The less dense regions were getting emptier. It was an incredibly slow process, taking hundreds of millions of years. But gravity is patient. Gravity never stops. Think of it like this. Imagine a perfectly calm pond with the faintest of ripples on its surface. Now imagine that each tiny ripple, each slight rise in the water, had its own gravity, pulling the surrounding water toward it. Over time, the ripples would grow. The peaks would get higher. The troughs would get deeper. That is what was happening in the dark universe. Gravity was amplifying the quantum whispers from the beginning of time, turning them into the scaffolding upon which all future structure would be built. This scaffolding, by the way, was shaped largely by something we cannot see and do not fully understand: dark matter. Dark matter does not emit light, does not absorb light, and does not interact with ordinary matter except through gravity. But it makes up about 27% of the total mass and energy of the universe, far more than ordinary matter, which accounts for only about 5%. Dark matter's gravity was the dominant force shaping the early structure of the cosmos, pulling ordinary matter into the web-like patterns that would eventually become the cosmic web of galaxies and galaxy clusters. The Dark Ages lasted for hundreds of millions of years. To a human, that is an incomprehensible stretch of time. Civilizations have risen and fallen in a few thousand years. The entire history of our species covers only a few 100,000. But the universe was in no hurry. It had a plan, written in the language of gravity and quantum mechanics, and it was executing that plan with infinite patience. In the darkness, in the silence, the seeds of everything were slowly germinating. Stars, galaxies, planets, life, all of it was being prepared, quietly, invisibly, in the vast dark nursery of the early cosmos. The first stars, cosmic dawn. Somewhere between 100 and 200 million years after the Big Bang, the darkness ended. In the densest regions of the universe, where gravity had pulled enough hydrogen gas together, the pressure and temperature at the center of these collapsing clouds became high enough to ignite nuclear fusion. And with that, the first stars were born. These first stars were nothing like our Sun. They were monsters. Hundreds of times more massive, millions of times more luminous, burning with a fierce blue-white light that had never been seen before in the history of the cosmos. Astronomers call them population 3 stars, and while we have never directly observed one, our models tell us what they must have been like: enormous, short-lived, and transformative. These stars burned through their hydrogen fuel in just a few million years, a blink of an eye compared to the billions of years our Sun will shine. But in their brief lives, they did something extraordinary. Deep in their cores, under pressures and temperatures that are difficult to fathom, they fused hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into neon, neon into silicon, and silicon into iron. For the first time, the universe contained elements heavier than lithium. The periodic table was being written, one fusion reaction at a time, in the hearts of dying stars. And when these massive stars exhausted their fuel, they died in spectacular fashion. They exploded as supernovae, the most powerful explosions in the universe, scattering their newly forged elements across space. Carbon, oxygen, nitrogen, iron, gold, all of it was flung outward in expanding shells of gas and dust, seeding the cosmos with the raw materials for planets, oceans, and life. This is a truth so profound that it bears repeating, especially as you drift toward sleep. The atoms in your body were made inside stars. The calcium in your bones, the iron in your blood, the oxygen you are breathing right now, all of it was forged in a stellar furnace billions of years ago and scattered across the universe by a dying star. You are not just in the universe. You are of the universe. You are stardust, arranged in the shape of a person, lying in the dark, listening to the story of your own origins. The death of the first stars was not an ending. It was a transformation. The elements they scattered became the building blocks for a new generation of stars, richer and more complex than the first. And around those new stars, the heavier elements began to clump together, forming rocky bodies, some small, some large. Over time, these would become asteroids, moons, and planets. The death of a star was the birth of a world. Every ending in this story contains the seed of a new beginning. That is one of the deepest patterns in the universe, and it is a pattern worth carrying with you as you fall asleep tonight. Galaxies form islands of light. As the first stars lived and died, the universe was becoming a more complex and beautiful place. The explosions of the first supernovae sent shockwaves through the surrounding gas, triggering the collapse of new clouds and the birth of new stars. These second-generation stars formed from gas that had been enriched with heavier elements, and they were different from their predecessors, smaller, longer-lived, and often surrounded by disks of gas and dust from which planets could form. Meanwhile, gravity continued its slow, steady work. The dark matter scaffolding that had been taking shape since the cosmic dark ages was now pulling in enormous quantities of gas. At the intersections of the dark matter web, where the density was highest, matter accumulated into vast structures. These were the first galaxies, collections of millions, then billions of stars, bound together by gravity and spinning slowly through the expanding universe. The earliest galaxies were small and irregular, nothing like the grand spirals and majestic ellipticals we see today. They were clumpy, chaotic, and often colliding with one another. But through these collisions, they grew. When two galaxies merged, their stars mixed, their gas combined, and new bursts of star formation lit up the darkness. Over hundreds of millions of years, these mergers built the galaxies up, layer by layer, collision by collision, into the magnificent structures we observe today. Our own galaxy, the Milky Way, was built this way. It is the product of countless mergers stretching back billions of years. And it is still growing. Right now, as you listen to these words, the Milky Way is slowly consuming several smaller galaxies, pulling them apart with its gravity and absorbing their stars. In about 4.5 billion years, it will merge with the Andromeda Galaxy, our nearest large neighbor, in a collision that will reshape both galaxies entirely. But that is a story for another night. The cosmic web. If you could zoom out far enough, far beyond individual galaxies, far beyond galaxy clusters, you would see the universe arranged in a vast, intricate pattern that astronomers call the cosmic web. It looks, in some ways, like a three-dimensional spider's web, or like the network of neurons in a brain, or like the pattern of soap bubbles packed together. Galaxies are not scattered randomly through space. They are arranged along filaments, long, thin threads of matter stretching across millions of light-years. Where filaments intersect, you find dense clusters of galaxies, hundreds or thousands of galaxies bound together by gravity. And between the filaments are enormous voids, regions of nearly empty space that can be hundreds of millions of light-years across. These voids are not truly empty, but they contain far less matter than the filaments and clusters. This entire structure, the filaments, the clusters, the voids, all of it grew from those tiny quantum fluctuations in the early universe. The pattern of the cosmic web was determined in the first fraction of a second after the Big Bang, written into the fabric of reality by quantum mechanics and then amplified by gravity over billions of years. The largest structures in the observable universe are echoes of the smallest possible variations in the quantum world. There is a deep peace in contemplating this. The universe, for all its size and complexity, grew from the simplest of beginnings. A tiny variation here, a slight excess of density there, and gravity did the rest. Patiently, inexorably, over billions of years, the cosmos shaped itself into the intricate, beautiful structure we see today. Nothing was rushed. Nothing was forced. The universe simply followed its own laws, and beauty emerged. Scientists have mapped portions of the cosmic web using surveys of millions of galaxies, and the maps are breathtaking. They reveal a universe that is both chaotic and ordered, random in its details but structured in its overall pattern. It is like looking at a coastline. Up close, the curves and inlets seem random. But step back, and you see patterns, rhythms, a kind of fractal beauty that repeats at every scale. The cosmic web has that same quality. It is endlessly complex, endlessly detailed, and endlessly beautiful. And we are part of it. Our Milky Way galaxy sits within one of these filaments, connected by threads of dark matter and gas to the larger cosmic structure. We are not isolated. We are woven into the fabric of the universe, connected to everything else by gravity, by history, by the shared origin of every atom in existence. When you look up at the stars, you are looking along the threads of the cosmic web, seeing your neighbors in this vast, interconnected structure. Dark energy, the universe accelerates. There is one more piece of this story that deserves to be told tonight, and it is perhaps the most mysterious of all. For most of the history of the universe, the expansion that began with the Big Bang was gradually slowing down. This makes intuitive sense. Gravity pulls matter together, so you would expect gravity to act as a brake on the expansion, slowing it over time. For billions of years, this is exactly what happened. But in 1998, two teams of astronomers made a discovery that shocked the world of physics. They were studying distant supernovae, using them as cosmic mile markers to measure the rate of the universe's expansion. And they found that the expansion was not slowing down. It was speeding up. The universe was accelerating. This was completely unexpected. Something was pushing the universe apart, counteracting the pull of gravity and driving the expansion faster and faster. Scientists gave this mysterious force a name, dark energy. And despite decades of research, we still do not know what it is. What we do know is that dark energy makes up about 68% of the total energy content of the universe. Ordinary matter, the stuff that makes up stars and planets and people, accounts for only about 5%. Dark matter makes up about 27%. And the remaining 68% is this mysterious dark energy, pushing the universe apart and accelerating its expansion. This means that the vast majority of the universe is made of things we do not understand. Only 5% of the cosmos is made of the familiar atoms and molecules that we can see and touch and study in our laboratories. The rest is dark, mysterious, and waiting to be understood. Far from being discouraging, this is one of the most exciting things about modern physics. There is so much left to discover. The universe is still full of secrets. And that, perhaps, is a comforting thought as you drift towards sleep. The universe is vast and largely unknown. There are deep mysteries that the greatest minds on Earth are still working to solve. And that means there is always more to wonder about, always more to learn, always more reasons to look up at the sky and feel that quiet sense of awe. The evidence, how we know what we know. You might be wondering how we can be so confident about events that happened nearly 14 billion years ago. It is a fair question, and the answer is one of the most beautiful aspects of science. We have multiple, independent lines of evidence, each pointing to the same conclusion. The first is the expansion of the universe itself. In 1929, the astronomer Edwin Hubble discovered that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it is receding. This is exactly what you would expect if the universe began as a single point and has been expanding ever since. If you mentally reverse the expansion, running the cosmic movie backward, everything converges to a single point. The second line of evidence is the cosmic microwave background radiation, which we discussed earlier. Its existence was predicted in the 1940s, long before it was discovered. When it was finally detected in 1965 by Arno Penzias and Robert Wilson, it confirmed one of the key predictions of the Big Bang theory. The universe should be filled with a faint afterglow from the moment it first became transparent. And it is. The third is the abundance of light elements. The Big Bang theory predicts very specific ratios of hydrogen, helium, and lithium that should have been produced in the first few minutes. When we measure these ratios in the oldest, most pristine parts of the universe, they match the predictions with remarkable precision. The chemistry of the cosmos is a fossil record of the Big Bang. And the fourth is the way structure has formed. The distribution of galaxies, the pattern of the cosmic web, the statistical properties of the cosmic microwave background, all of these are consistent with a universe that began in a hot, dense state and has been expanding and cooling ever since. Computer simulations that start with the conditions predicted by the Big Bang Theory and run them forward in time produce universes that look strikingly like our own. Each of these lines of evidence, on its own, would be compelling. Together, they form an overwhelming case. The Big Bang is not just a hypothesis. It is one of the most well-supported theories in all of science. What we still don't know. And yet, for all that we have learned, there is so much that remains mysterious. Science is an ongoing journey, and the story of the universe's beginning is far from complete. We do not know what happened in the very first instant, before inflation began. Our theories break down in that extreme environment, where the temperature and density were so high that quantum mechanics and gravity become entangled in ways we do not yet understand. To truly understand that first moment, we will need a theory of quantum gravity, a theory that unifies the very large and the very small. That theory does not yet exist, although many brilliant physicists are working on it. We do not know what the inflaton field is, or why inflation started, or exactly how it ended. We do not know why there was a slight excess of matter over antimatter. We do not know what dark matter is made of, despite knowing that it makes up most of the matter in the universe. And we do not know what dark energy is, despite knowing that it makes up most of the energy in the universe. These are not failures of science. They are invitations. They are the open questions that will drive the next generation of discoveries. And they remind us that the universe is far more complex and far more wonderful than we have yet been able to comprehend. There is a certain comfort in not knowing everything. It means the story is not over. It means there are still surprises waiting for us. It means that the universe will continue to astonish and humble us for as long as we are willing to look. A reflection, your place in the story. So here you are, lying in the dark, at the end of a long day, listening to the story of how everything began. And you might be wondering where you fit into all of this. You are, after all, a very small part of a very large universe. But consider this. You are made of atoms that were forged in the cores of ancient stars. The hydrogen in your body has been around since the first few minutes after the Big Bang. The carbon in your cells was fused in a star that exploded billions of years before our sun was born. The iron in your blood was created in the final moments of a massive star's life, in the unimaginable violence of a supernova. Every atom in your body has a history that stretches back to the very beginning of time. You are not separate from the universe. You are a part of it. You are the universe experiencing itself, wondering about itself, telling itself the story of its own creation. That is not a metaphor. It is literally true. The atoms that make up your brain, the ones that are right now processing these words and forming thoughts and drifting toward sleep, are the same atoms that were present at the Big Bang, rearranged over billions of years into something that can think and wonder and dream. The universe began as a single point of infinite density and temperature. It expanded, it cooled, it formed particles, then atoms, then stars, then galaxies, then planets. And on at least one of those planets, orbiting an ordinary star in an ordinary galaxy, those atoms arranged themselves into something extraordinary, a living being that can look up at the night sky and ask, how did all of this begin? That is you. That is the miracle. Not a miracle in any supernatural sense, but in the deepest, most profound sense of the word. Against astronomical odds, the universe produced something that can understand the universe. And here you are, doing exactly that, even as sleep gently reaches for you. Closing, letting go. The universe is nearly 14 billion years old. It has been expanding since the first instant, cooling and growing more complex with every passing moment. From a single, impossibly hot point, it has become a vast cosmos filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, many of them orbited by planets, some of them, perhaps many of them, harboring life. The story of how the universe began is the story of how everything you know and love came to be. The ground beneath you, the air around you, the stars above you, the blood in your veins, all of it began in that first blazing moment, nearly 14 billion years ago. And the story is not over. The universe is still expanding, still evolving, still producing new stars and new planets. Dark energy is still pushing the cosmos apart. Somewhere, right now, a cloud of gas is collapsing under its own gravity, and a new star is about to be born. Somewhere, a star is dying, scattering its elements into space, seeding the raw materials for future worlds. The universe is alive with creation and transformation, even as you lie here, perfectly still. You do not need to hold on to any of this. The universe will still be here in the morning. The stars will still be shining. The cosmic microwave background will still be whispering its ancient story. You can let go now. Let the weight of these ideas settle into your mind like dust settling on a still pond. Let your thoughts slow. Let your breathing deepen. Think of the universe as a great, slow exhalation. It began in a single, compressed instant of unimaginable energy, and it has been releasing that energy ever since, spreading out, cooling down, growing more complex and more beautiful with every passing moment. Stars are born and die. Galaxies spin and merge. Elements are forged and scattered. And out of all of that, life emerges, consciousness emerges, and the universe becomes aware of itself. That is the story. That is the whole story, from the first fraction of a second to this very moment, as you lie here, breathing, thinking, slowly letting go. You are a child of the cosmos, made of star stuff, lying on a small planet, orbiting an ordinary star, in one arm of a spiral galaxy, in a universe that began with a whisper of energy and has been unfolding ever since. The hydrogen atoms in the water molecules in your body have been around for nearly 14 billion years. They have been part of stars, part of nebulae, part of the vast clouds of gas that drifted through the dark ages before the first star was born. They have traveled across the cosmos, and now, for this brief, beautiful moment, they are part of you. And when you are gone, they will continue their journey, becoming part of something else, something new, something the universe has not yet imagined. There is nothing to worry about. There is nothing to do. Just breathe and know that you are part of something vast, something ancient, something ongoing. The universe is still unfolding. New chapters are still being written. And you, in your own small way, are one of those chapters. Close your eyes. The universe will carry you from here. Good night.